Let me start recording. All right. So let's take a look. All the reactions. Okay. Again, these are some are summarized reactions, some are real case examples, but it shows you what we have learned starting chapter 6 about organic reactions and why we got those results and what the mechanism is. All right. So first, in chapter 6, alkenes, we have most reactions are electrophilic substitution. I'm sorry, electrophilic addition reactions. Now, the very first electrophilic addition reaction is adding HBr to an alkene. And we know the reaction undergoes a carbocation intermediate. So the product is Marx product. The hydrogen added to the less substituted, the bromine added to the more substituted, and that's the Marx product. Okay, Marx product. And very similarly, if we add water instead of HBr, we can get an alcohol. Also, the alcohol is Marx alcohol. And very similarly, the reaction undergoes carbocation intermediate. And in order to add water, we have to use an acid as a catalyst. Now, let me ask you guys, both reactions, what is the first step? In both of these reactions, what is the first step? Guys, in both reactions, what is the first step? When you see a reaction, not only you need to understand the products, you have to know, hey, put the mechanism in your mind. What is the first step, guys?
Is it pronation?
The pronation, that's very good. The first reaction, HBr, it has a proton. So that's why we can carry out the reaction with the HBr by itself even. You can do it without a solvent. But in the second reaction, the reason we had acid catalyst is because we need a proton. That's the electrophile. So both reactions is, okay, both reactions is pronated. That's why you have a carbocation. The first step is pronation. The double bond is the nucleophile. The proton is the nucleophile. That's the same, right? The third reaction is adding this alkene with HBr. And you can see here, instead of getting addition on the double bond, you can see the HBr is added in different places. And we know this reaction happens through rearrangement of carbocation. So basically, what you got is this carbocation and this carbocation rearranged into this carbocation through 1,2 shift. Okay, through 1,2 shift. So that means electrophilic addition of HBr, there is a possibility you get an rearrangement product if a secondary carbocation can rearrange to generate a more stable tertiary carbocation. Okay, this is one of the case. Okay, you have to, if that's the case, you will definitely get a rearranged product. And that's the drawback of using electrophilic addition, because if the structure is like that, you will get a rearranged product. Okay, the fourth reaction is adding Br2. Okay, adding Br2. And we know the reaction undergoes bridged bromonium ion intermediate, and the other Br minus open the bridged bromonium ion intermediate ring from the backside. So you will get a trans product. You can see that two BRs are on the opposite side of the ring. I use this example because I want to show you the trans. Why? Because open up the bromonium ion intermediate ring is from the backside of the ring. So we get an anti-stereo selectivity. You end up with a trans product. Now, when the ring is formed, it can form both on the top of the double bond or from the bottom of the double bond, meaning when the double bond serves as a nucleophile, react with Br. The double bond can react the Br from the top or from the bottom or from either side. So that's why in the end, you get a pair of enantiomers. The product is racemic. Okay, 50%, 50% chance because bottom side, both faces get equal chance. But either product, each one is anti. Okay, you get each one is trans. Okay, next, adding Br in the presence of water. The product is hydrohalogen, or this one is hydrobromine, meaning after forming the bridged bromonium ion intermediate, Br minus does not open the ring. Instead, water will open the bromonium ion ring. So that is why you're adding a Br and adding a water. This OH came from where? Came from water. Again, this intermediate, these two reactions, intermediate is the same. Bridged bromonium ion intermediate. Let me show you guys. Okay, bridged bromonium ion. Both have the same intermediate because you both have Br. But the difference is in the first reaction, Br minus opens up. The second reaction, water open up the ring. That's why you get dibromo product or hydrobromide. Okay, hydrobromide. Now, when you have water in presence, the sterol selectivity is also trans because open up the bridged bromonium ion ring is always from the backside. So the trans sterol selectivity is the same. You can see both products are trans. However, this one adds a little more about the regioselectivity is the water will be added to the more substituted carbon because that carbon has more carbocation character. You can see in both products, the water is added to the more substituted carbon. But water and Br are trans. You see, guys, see that? OH and Br are trans in either one, trans. That is adding Br2. Both are adding Br2. This first case is Br and Br are added. The second case is instead of opening the ring with Br, we have water to open up the ring. Does it make sense, guys?
Yes.
Or do you guys recall these reactions? Okay, these are from chapter 6. Now, next is adding, mercury or mercury 2+ serves as the electrophile. And we call this reaction oxymercuration followed by reduction. Okay, the first step is oxymercuration. The second step, sodium boron hydride, is reduction. And this reaction undergoes this intermediate. Okay, undergoes this intermediate. And because of that, when water attacks to open this bridged ring, water attacks this carbon, okay, of this carbon. So that means after you reduce the mercury, you get an alcohol, and this alcohol is also Marx product. Why? Because the OH is added to the more substituted carbon, because that carbon has more carbocation character. So someone take a look. What's the similar between these two reactions? I'm drawing an arrow here. I'm gonna use a different color. Do you see, guys, see these two reactions? They got the same product, right? One reaction is hydration, adding water. The second reaction is also basically adding water, but takes 2 steps. So both reactions, you get the same product, a more substituted alcohol, Marx product. But The second reaction using mercury, there is a very good advantage. That is, the product will not be a rearrangement product. So if your substrate has a potential of undergoing rearrangement using oxymercuration followed by reduction, your product will be the one you wanted. You will not see any rearrangement product. That is the advantage of using oxymercuration. So for example, if I want to use this substrate, if I want to add water to the substrate, I cannot use hydration. Why? Because we know this substrate will undergo rearrangement. So if I want an alcohol, if I want OH added to the secondary carbon, I need to carry out the reaction using oxymercuration followed by reduction. Okay, again, anyway, oxymercuration followed by reduction, you get a Marx product. It serves like a hydration. You get the same result as hydration, but you will not see any rearrangement without rearrangement. Okay, next reaction is hydroboration followed by oxidation. I think you guys now should be very familiar with this reaction because I even gave you a paper on this reaction. Okay, hydroboration followed by oxidation. This reaction basically also serves as add water. Hydration, just like hydration, I mean, results, end of the results is hydration. But there is some difference between this hydration and the ones we learned before. First is the addition of H and OH is syn stereoselectivity, meaning you get a cis product. You can see that OH and H are added on the same side of the double bond, either on the top side or the bottom side. That's the first difference. It's syn addition. Number two is OH. You can see that now is added to the less substituted carbon. In the reaction above, in the reaction right above, you can see that the OH is added to what? To the more substituted carbon. But in this case, OH is added to the less substituted carbon. We call that non-Marx product. Okay, non-Marx product. The reason we have a non-Marx product is because this carbon is less crowded, less carbon like boron. Okay, boron is actually added to that carbon because boron is a bigger atom. So steric factor is dominant here. That carbon is less crowded, less substituted, less crowded, like boron. And then in the end, boron is converted to OH in oxidation step. So hydrogen is added to that carbon, boron is added to that carbon. They're added at the same time. That's why you're syn. Okay, we have syn stereoselective because they're added at the same time. So basically, these two came from this intermediate. Okay, this intermediate. For example, hydrogen Br2. Okay, boron is added to that carbon. Okay, of course, this guy came from. Okay, this guy came from that intermediate. Okay, boron is added to the less substituted carbon. That's why you get OH on the less substituted carbon. That is electrophilic substitution. And of course, we added hydroboration and oxidation. Do you guys have any questions here? I will give you the file. Don't worry. I don't know how to review, so this is what I can think of. I made this file in the morning. Okay, I draw this structure myself. Okay, in the morning. Do you have any questions, guys? Okay, next, still chapter 6, we have oxidation and reduction reactions. Okay, we have 2 oxidation and 1 reduction. The first oxidation is treating alkene with osmium oxide. We can get vincinyl diol, 1,2-diol. Basically convert the double bond to 2 alcohol, 2 OH. And the reaction is syn stereoselectivity. Means you get a cis diol. In this case, because the diol is a methyl product, so there's no racemic because either way is the same. But it provides you when the osmine adds to the double bond, it can add to both sides. So you actually got OH on the same side or on the bottom side, but because the product is methyl, so we only show one structure. Okay, structure. So that's first oxidation, treating with osmium oxide, of course, followed by reduction, a little using a sodium hydrogen sulfide can reduce the osmium complex. We get a vicinal diol, 1,2 diol. The second oxidation is treating an alkene with ozone, followed by reduction with dimethyl sulfide. We can cleave the double bond and generate a 2 carbonyl compound. Of course, this is a cyclic alkene. So after cleave the double bond, we get a dialdehyde because we have 2 double bond, okay, 2 carbonyl group. Okay, whether you get a ketone or get an aldehyde depends whether you have hydrogen on the carbon, on the double bond carbon. This case, we have a hydrogen on each one of these 2 carbon. That's why we end up with 2 aldehydes. If you don't, you add with ketone. And always remember, you cleave the double bond, you add oxygen, CO double bond. And finally, the reduction of alkene will produce alkane. Basically, you hydrogenate it. The reaction must be catalyzed by a metal catalyst. And the stereoselectivity is syn, means the hydrogen are added on the same face of the double bond. Okay, either top or bottom states. Again, the product is methyl. That's why we only show one structure. Okay, show one structure. Does it make sense, guys? I not only provide you with the reaction, but also summarize what is the selectivity, what is the reduced selectivity, what is the stereoselectivity for you to take a look. Please let me know if you have any questions. Guys? Does it make sense? Everything?
Yes, thank you.
Okay, let's move on to chapter 7. Okay, to chapter 7. Alkyne. Okay, alkyne. First reaction for alkyne is sp carbon CH bond. The pKa, that proton on sp carbon is slightly acidic. Anybody remember what is the pKa?
Is it 4.5 or like 5?
No. What is the pKa for sp?
Oh, 50.
How many?
Is it 50?
No.
16.
No, 16 is for hydroxide. For hydroxy, what is the pKa? Think about it. 25. Okay, 25. The pKa is around 25. So because the pKa is 25, if I use a strong base, I can remove the proton of a terminal alkyne. Again, this one only happens when the alkyne is terminal, means what? 1, 2. Okay, 1, 2 carbon. That's why you can have a hydrogen. Otherwise, there won't be hydrogen for triple bond. Okay, strong base such as sodium amide, or you can use sodium hydride. Sorry, let me erase it. Okay, you can use sodium hydride. Both are stronger base, stronger enough bases to remove, okay, to remove a proton from the terminal alkyne. So basically, after removal, you get a C minus. Okay, C minus, a carbanion intermediate. C minus is a strong nucleophile. C minus is a very nice nucleophile. So it can serve as a nucleophile to what? To do a substitution reaction. And the most useful substitution is if I use a primary halide, such as primary bromide, So the carbon C- can substitute the bromine. We have learned now, I mean, when we learn chapter 7, we haven't learned chapter 9 yet. Now we know that this is SN2 reaction. That's why primary works best. So C- attacks the electrophile, Br- leaves. We can actually add a few carbons on the C- on the triple bond. Okay, this part is the added one. You can see that's the new bond formed, the one I put a dash on. So this is a very good strategy to make CC bond, to elongate a carbon chain, or I can say to make a terminal alkyne to a what? Internal alkyne, because I change the proton now to a what? To a carbon. But of course, I need to remove the proton, make a C-, and do a substitution. I can change, okay, I can change an terminal alkyne to an internal alkyne. So that's the first reaction. Wow, how do we use the acidity of that proton? I can convert terminal alkyne into a nucleophile. Then I can do a substitution. Again, this reaction works the best when you have a primary, okay, primary halide. Okay, primary halide. Next reaction is, how do we prepare a CC triple bond? We usually start with a dibromoalkane. Okay, dibromoalkane. And of course, you want to ask, how do we get dibromoalkane? We can actually prepare from an alkene. Treating alkene with Br2, I can get a dibromoalkane. So this shows you the whole sequence. If I start with an alkene, I treat it with Br2, I can prepare a dibromoalkane. And then if I treat the dibromoalkane with 2 equivalents of strong base, such as sodium amide, I can remove 2 HBr. Basically, I kind of sort of remove 2 HBr from that structure to give you a triple bond. That's how we prepare. Treating a dibromoalkane with 2 equivalents of strong base, removing 2 HBr to get the triple bond. Now, in this particular case, because the product triple bond is a terminal triple bond, so the terminal, we know from the beginning, terminal CH is acidic. So this terminal product will consume one further equivalent of the base. So technically speaking, you need at least 3 equivalents of the base to get the C-. And then if you want the alkene, you can treat the C- with water to get the final product. I'm just showing you what happened here. If you only use 2 equivalent base, you won't have enough. Why? Because this product will consume some of the base. So that's why you need 3 equivalent base. And in the end, you get the C-. And then you treat the C- with either weak acid or even water, because this is stronger base than OH-. You can get the alkyne you wanted. Okay, alkyne. You can see there's multiple steps. Again, this is a terminal alkyne. You have to use 3 equivalent. Okay, 3 equivalent. Next is, if I treat alkyne with 1 mole of Br2, I can add Br2 to the triple bond to get a dibromoalkene. But the reaction is stereoselective, and these 2 bromine will be trans. Okay, will be trans. The reason is also the bridged bromonium ion intermediate and opening the rings from the backside. That's why you get a trans. Of course, adding Br- to the reactant mixture will increase the stereoselectivity, make more trans. Okay, make the trans become more dominant. This is treating with 1 Br2, 1 mole of Br2. Again, trans alkene. If I treat it with 2 mole, of course, you convert the triple bond to a single bond, you get tetrabromo product. Okay, tetrabromo product. That's very straightforward. Questions, guys? Do you guys remember these reactions? Recall anything? Or you have no idea what I'm talking about, at least, guys? Can you tell me? Hello, guys.
I remember.
Okay, thank you. Okay, thank you. I just want to double check if you guys really remember anything or have no. At least you know what I'm talking about. All right. Now, next is adding HBr to alkyne. Okay, adding HBr to alkyne. Very similar to the one we've seen before. Adding HBr to alkyne follows a carbocation intermediate. So the reaction is Marx. Okay, the reaction is Marx. Okay, this is not non-Marx, it's Marx. Okay, I'll change that, it's Marx. Okay, I maybe copy and paste. Okay, I'll change that. Hold on, let me change it right away. Okay, I know there's some mistake. I made this in the morning, so I don't wanna, when I send you the file will be the updated, most updated one when we go over everything. Where is it? Here. One second. Okay, this is Marx product because it's carbocation intermediate. Marx. There we go. Okay. Marx means the Br is added to the more substituted carbon. Why? Because here is more carbocation. Okay, this carbon is more carbocation intermediate. Now, if I add another molecule of HBr, the addition is also Marx. You end up with 2 Br on the same carbon. So both bromine will be added to the more substituted carbocation. Now, this intermediate is a little unique. I want to show you. After getting the proton from HBr, the second HBr, we got this intermediate. We got this intermediate. Of course, we know this is a tertiary, kind of like a tertiary carbocation, is more stable, but there's another factor makes the second HBr addition follow Marx is Br actually can stabilize the carbocation using resonance. Okay, using resonance. So when the C is on this carbon, okay, C is on this, when the C plus is on this carbon, it's much more stable than primary, secondary, tertiary stable because the Br has lone pair can, of course, Br is from the first HBr, has lone pair can further stabilize the carbocation through resonance. You can see that these two are resonance structures. Okay, let me circle. These two are resonance structures. And because of that, the second Br, when the second Br added, second Br is preferred to be added to the same carbon. Okay, that's one factor. Further factor, other than primary, second, tertiary carbocation stability, is because Br can stabilize the carbocation. So you end up with dibromo product adding 2 HBr, and these 2 bromine will be on the same carbon, more substitute carbon. Okay, the reaction follows non-Marx. Okay, non-Marx rule. Next, treating alkyne with boron will also give us hydroboration product. But here is the difference than what we learned from chapter 6. The first difference is if you want to use boron BH3, the alkyne must be internal alkyne, like this guy. Okay, you cannot treat terminal alkyne with boron. The reaction will be messed up. Has to be internal. Okay, of course, treating boron with internal alkyne with boron, you initially got this guy, Br2. Okay, B and H added to the same side of the triple bond, you get a cis product. Okay, you can see that cis product. Of course, after oxidation using hydrogen peroxide and sodium hydroxide, you convert the B to OH. Okay, let me draw it better. Okay, initially, you got this. H, B, B, Br2. And then treating with hydrogen peroxide, you convert the B to H. And after convert B to H, you see that this structure is called an enol. It will tautomerize to a ketone. Okay, of course, the equilibrium favors the right. But again, if you want to use BH3, it has to be internal. If you use BH3 with terminal, the reaction will further react because this is an alkene, remember. The alkene will also use with BH3. The reason the reaction stops here is because the terminal, it's more crowded. That's why the reaction stops here at the alkene stage. That's why you can get an enol. The double bond is not touched. The reason is the double bond is internal. It's crowded. The B will not further react anymore. So if we have a terminal alkyne, if we want to carry out hydroboration and oxidation, you have to use a crowded, or we call sterically hindered boring reagent. This is the steric hindered one. Okay, Si(A)(2BH), only one boron and one H. Okay, only one hydrogen, not BH3. Because this is steric hindered, the reaction can stop at the alkene stage. You can still we get an alkene. Okay, still we get an alkene. And after tautomerization, the enol becomes carbonyl compound. Now, because it's terminal, so we do have a regio selectivity. Okay, because terminal means they're different. One is CH, one is C. We do have a regio selectivity in which the B will be added to the less substituted carbon. So the OH is added to the less substituted carbon. So this is what happened here. After you add B, you got this. BSiA2. Okay, got this. The boron is added to the less substituted carbon. Why? Because boron is a bigger atom. We said earlier, it likes less crowded carbon. So the reaction is non-Marx product. Okay, B is less substituted, means OH is less substituted. If OH is substituted, you get an aldehyde. Okay, because OH is at the terminal carbon. Okay, you get an aldehyde. So these two are hydroboration of alkyne. Internal, you use BH3. Terminal, you use the sterically hindered boron. Next reaction is treating alkyne with water. And of course, the reaction has to be catalyzed by both an acid and the Lewis acid, mercury 2 sulfate and sulfuric acid. We can add water to the triple bond. But in this case, the reaction undergoes kind of a carbocation intermediate. So the reaction is Marx. Okay, here, the reaction is Marx. It's not non-Marx, it's Marx. Why? Because the reaction undergoes carbocation intermediate. So you can see that OH adds to what? More substituted carbon now, because it is hydration. If OH adds to more substituted carbon, we get a ketone after the enol tautomerize. Okay, tautomerize. So these three reactions are actually the one shows you how can we convert an alkyne to a carbonyl compound, either a ketone or an aldehyde. Depends on what you start. If you want to treat with boron internal or treat with hydration, you get a ketone because Marx. If you treat treat terminal with steric hindered boron, you get aldehyde because non-Marx. Okay, because non-Marx. Depends on what you want. So this reaction shows you how to convert alkyne to carbonyl compound. Okay, carbonyl compound. Any questions, guys? Next, reduction of alkyne. Okay, reduction of alkyne. Reduction means add hydrogen. Okay, add hydrogen. The first reduction is full hydrogenation, meaning we have enough hydrogen in excess of hydrogen under metal catalyst, palladium, platinum, or nickel. We can saturate triple bond to a what? To an alkene. Very simple, straightforward. But what if I want to convert an alkyne to alkene, meaning I only want to add 1 mole of hydrogen. I want the reaction to stop at the alkene stage. Here are the 3 methods we use. The first 2 give cis product, cis alkene. The third one get trans alkene. So let's take a look at the first 2. The first method to give a cis alkene is hydrogenation using a toxicated catalyst called Lindler catalyst. The toxic catalyst means the reaction will not further moving on to alkane stage. It will stop at an alkene. But because it's hydrogenation, remember hydrogenation is the molecule stay on the surface of the metal. So they start on the same side. So these 2 hydrogen will be added on the same side. Cis. Another method is hydroboration followed by an acid. Okay, hydroboration. We know hydroboration. If I treat a terminal internal alkyne with BH3, I get what? I get this guy. Okay, I get this guy. You can see that why we have a cis this time, because H and B are at the same site. Again, this is internal, I can use BH3. But instead of doing high oxidation that we shown previously, we treat this guy with an acid. A hydrogen will replace the B, sterol selectivity. So in the end, you got 2 hydrogen on the same side because boron is on the same side with the hydrogen. So 2 hydrogen on the same side. We call this reaction hydroboration followed by, it's called protonolysis. Okay, protonolysis. 2-step, treating with hydroboration and then followed by acetic acid. You can replace the B with a hydrogen. The third reduction is treating alkyne with sodium metal in liquid ammonia. And this system basically provides electrons to reduce the alkyne. And because electron needs to be further away from each other, that's why we get a trans product. Again, this reaction is reduced by electrons, the electrons from sodium. Sodium actually provides the electron to reduce the alkyne, to reach the triple bond. That's why you get a trans. So this reaction shows you how do we reduce an alkyne to an alkene, and whether we need cis or trans, we use different system. Cis, we have 2 methods, hydrogenation, Lindner's catalyst, or hydroboration followed by protonolysis. Okay, both can give you cis. Trans, of course, we use.
So if for hydroboration,
I'm sorry, go ahead.
For hydroboration, is it if it's terminal alkene, do we still use?
Can do that.
Can
yes.
we?
If you use terminal alkyne, you have to use the stereochemical boring, but you can still do the same reaction. Yes.
Okay.
Yes, but if it is terminal, there's no cis or trans, right? Because terminal has 2 alkynes. I mean, there won't be. We don't care about cis or trans if it is terminal. Yes, but still, if you want to use the same way for terminal, okay, let me write it for you if you want to know.
Do we still add the same acid?
Yes, acetic acid. Okay. Instead of using boron, you have to use this guy, and followed by acetic acid, you will get alkene. But again, this one, there's no cis or trans because there's 2 hydrogen here. You can see that. right? So there's no cis or trans, but yes, you can still use the same way, the same reaction sequence called hydroboration followed by pyrolysis. Instead of using pH3, you use a steric-candidated borane, but everything is the same. The reaction is still the same. Yes. Good question. Any other questions, guys? Again, the reason this reaction is cis because here is cis. Hydroboration is cis. That's why you get a cis product. Okay, cis product. Questions, guys? Okay, move on. Chapter 8, radical reactions. Okay, radical reactions. First, radical reactions normally is under UV light or heating. Most times UV light, because heating is hard to control under higher temperature is always bad for organic reactions. Okay, so mostly under UV light. Why? Because UV light can split Br2 homolytically to give us Br radical. That's how we start the reaction. Now, what's most important about radical reaction is they are regioselective. Regio means because tertiary radical is more stable than secondary radical is more stable than primary radical. So if there is different types of hydrogens, the substitution will happen on tertiary over secondary over primary. In this case, you can see that I'll give you an example. The substitution happens on primary. I'm sorry, on secondary, because regioselective. Secondary radical is more stable. And number two, because radical is sp2 hybridized. So when it comes to substitution, remember you first got this radical. Okay, first you got this radical. Okay, the intermediate is this radical. Okay, it's radical. This radical is flat. So when Br approaches, it can approach from either side. Okay, can approach here. Can approach here. That's why you get a pair of enantiomers, and the product will be racemic. So that's regioselective and also stereoselective. That's the result for radical reactions. Of course, make sure you can write down the mechanism, medical mechanism. Next is if we have allylic carbon is very good at radical reaction because allylic radical is very stable. So if we want to do a allylic bromination, we can use a unique reagent called NBS. Again, NBS look like this. That's NBS, N-bromosuccinimide. Okay, N-bromosuccinimide. And still under UV light, you will have allylic bromination. Okay, remember what is allylic carbon? Allylic carbon is the carbon next to the double bond. So here we have two allylic carbons. Of course, these are equivalent. Now, one thing to be careful about allylic reaction is because allylic radical has resonance structures. For example, if I have a allylic radical here, the allylic radical can resonance. So basically, when you have allylic bromination, you can expect bromination happens on carbon number 1 and 3 because that's where the allylic radical will be shifting because of resonance. So here you can see that if I treat the NBS with this alkene, I get two products. Both are allylic. And carbon number 1 and carbon number 3. You can see carbon number 1 and carbon number 3. Both are potential products. Of course, the major product will be the one with more substitution alkene. This alkene is more substituted. This is the major product. But there may be multiple products because allylic carbon is resonance stability. And finally, when we talk about radical reactions, we have a way to control the regional selectivity for adding hydrogen bromide. I put two reactions together for you to compare. If we treat an alkene with hydrogen bromide, like we see before, we know the reaction is Marx addition, BRS to the more substituted carbon. But if I treat alkene with HBr and I'll add peroxide, okay, again, peroxide has the structure like this. Okay, this is one of the peroxide looks like. Okay, peroxide. Then the reaction will undergo through radical mechanism. Undergo through mechanism, the result is a non-Marx product. You can see that with peroxide, non-Marx. Without peroxide, Marx. Why do we have that difference? Because these two reactions happen through different intermediate. Okay, let me show you these two intermediate. You will understand why there's a difference. Again, guys, whenever you see a reaction, the best to understand the reaction is put the mechanism in your brain. So you can write down the intermediate. That's how you understand the reaction. All right. If I treat HBr with peroxide, the reaction undergoes radical mechanism. So Br is added first. When Br adds first, in order to get the tertiary radical, Br adds to the less substituted carbon. This is the intermediate for adding HBr with peroxide. Br is added first as radical. And in order to get a more stable radical, Br adds to the less substituted carbon. That's why we get non-Marx product. If I add HBr without peroxide, proton is added first. Remember he said earlier, this is electrophilic addition. When proton is added, we get what? We get, okay, let me draw it similar to the one shows in substrate. Proton is added first. Hydrogen is added first. And you get a more stable carbocation. In order to get a more stable carbocation, proton is added to what? The less substituted carbon. So the reason is, of course, we get two different intermediates. Both intermediates needs to be more stable one, means the tertiary. But the difference is in peroxide reaction, Br radical is added first. You get a more stable tertiary radical. When you have electrophilic addition without peroxide, pronation happens first. You get a more stable carbocation. That makes one reaction Marx, one reaction non-Marx. Okay, so these are reaction in chapter 8. Does it make sense, guys? Does everything clear now? Looks more clear? I don't know. That's the best way I can summarize. I can say, guys, if you could summarize like this and understand like this, that means you understand the chapter. I don't know how good you can summarize these reactions. Any questions?
This is helpful. Thank you.
Thank you. I'll definitely email this to you or post on the website. You can take a look. Okay, you can use it in your test. I don't mind. Like I said, I hope by the last final you guys are satisfied. I am sorry, some of you still may not be satisfied in the third test, but hopefully in the last test, practice with your OWL homework. Take everything with it. You have what, a week, almost a week, practice with the OWL. And when you comes to something you don't understand, hey, why the question gives that? Go to the notes. Okay, go to the notes. Don't get stuck with something you think because of the system. Something may, but not all the questions. There may be 1 out of 10 there are questions you get stuck. Hey, no matter how I draw it, it's not correct, and I'm pretty sure I'm right. Then move on. I mean, when it regards to practice, move on. In the test, of course, try your best. But when it comes to practice, don't get stuck spending an hour to drive yourself crazy on one single question. As long as you know how to do it, move on. Sometimes it may be the system. I've seen that before, but not all the time. Okay, maybe 1 out of 10, 1 out of 20. It's not that common, but still it happens. All right, chapter 9. Okay, chapter 9 is about, most difficult thing is about, again, is to determine which reaction is dominant. How do we determine what product we get between these 4 types of reactions? Between 2 types first, substitution versus elimination. And when it comes to substitution, we have SN1 and SN2. When it comes to elimination, we have E1 and E2. So the question is, how do we determine which one is dominant? Or if we have multiple products, which one is the major product? Okay, I want to go over this thing again with you, and then we use our test, some test example from our test to show you more example, to explain to you how to apply these rules. I think the table from your book is pretty good regarding summarizing these things. So let's take a look at them again. When it comes to these competing reaction, you first look at the substrate. Okay, you first look at substrate. If the substrate is primary, okay, if the substrate is primary, there's never gonna be SN1 or E1. So it's impossible unless you have what? You have allylic or benzylic, that's different. But for primary, you will not see SN1 or E1. So basically means you either have SN2 product or E2 product. When you have a strong nucleophile but a weak base, strong nucleophile means what? Substitution profile. So you get SN2. If you have a weak nucleophile and a strong base, what is the weak nucleophile and a strong base? A hindered base. Hindered base means what? It's not a good nucleophile, but it's a strong base. Then you have E2. So very clear. Strong nucleophile, weak base, SN2 preferred. Weak nucleophile, strong base, E2 preferred. If you have a sterically hindered base like this base, there's no SN1 reaction. There's no SN2 reaction because it's impossible because it's steric hindered. Then you only have E2. If you have a good nucleophile and a good base as well, then you have both products. SN2 is preferred. SN2 is more dominant. Okay, here is this simplified version. Like we said, I put in your practice as well. If all things are equal, SN2 is more dominant than E2. That means if you have a good nucleophile and a good base, they're both good. Then SN2 is, you have SN2 product, you have E2 product, but SN2 is more than E2. Does it make sense, guys?
Yes.
Now, let's go to tertiary. Okay, go to tertiary. If you have tertiary substrate, again, you look at the substrate first. If you have a tertiary structure, there's no SN2. Okay, there's no SN2. You know tertiary is impossible for SN2. So you have 3 options, E2, SN1, and E1. How do we determine? E2 means you have a strong base. If you have a strong base, you have a tertiary, you have E2. Because again, you have no SN2. Strong base, E2 for tertiary. If you have a weak base and a weak nucleophile, then you have SN1 and E2. They're both competing. Okay, SN1, E1, weak base, weak nucleophile, they're both competing. I can't say which one is more. Maybe still substitution is more. Okay, substitution more, you can see that substitution is more. Okay, substitution is still more than elimination, but weak nucleophile, weak base, E1 and SN1. But if you have a strong base, E2 for tertiary. In that case, you don't even need a hindered base because tertiary hindered already. Any base, strong base will promote E2, elimination. Lastly is secondary. Okay, you have all competing. That's the most hard to judge, but still You have a lot of clues because the condition will tell you a lot. If we have a secondary, you have all reaction possible, but very similar like we discussed. If you have a strong nucleophile and a weak base, you will have SN2 dominant. If you have a weak nucleophile but a strong base, you have E2 dominant. If you have a hindered base, E2 will be more dominant. If you are both strong nucleophile and both base, strong base, then both will be existent. SN2 will be more dominant than E2. And finally, if you have weak nucleophile and weak base, such as a solvent, for example, water, methanol, a solvent, I mean, they're weak nucleophile, weak base, then you are competing with SN1 and E1. Still, substitution is more dominant than elimination. So that's how we determine. This is the full version of what we study in the book. And this is the simplified version I put on your test. Okay, put on your test. So again, look at the substrate first, then rule out something that's not even possible. Then we move on to the condition. Okay, move on to condition. So with that, let's do a few practice using the keys of your test. Is this the key? No, that's chapter 9. Here, this is your test. Okay, I'll go over some questions if you want, but here, these are the 3 we're talking about. See, we have 3 substrate. Let's take one at a time. We have a secondary here. We know secondary, there's all possible, but we have a what? Weak nucleophile and weak base. Do you see that? The solvent, nothing else. Ethanol, solvent. If it is a weak nucleophile, we have what? SN1 and E1, nothing else. Because there's no way you have E2. There's no way you have SN2 because they both are weak. And if we have SN1 and E1, then we have what? Substitution product and elimination product. Substitution major, elimination minor. Does it make sense, guys? See that? Use the guideline from your book, and you can easily determine for the first one. Secondary substrate, weak nucleophile, weak base. Then we're talking about SN1 and E1. SN1 is more dominant than E1. Then we have both. SN1 is major product, E1 is the minor product. Is the minor product. The second case, we have secondary as well. But what is the base, guys? Take a look. A sterically hindered base and a sterically hindered strong base. So we have what? E2. Secondary, hindered base, no substitution. No substitution means what? Means we have elimination. And this is a strong base, what elimination? E2 elimination. So all the products are E2 products. Of course, this one is the major because this one is more substituted, trans, more substituted. This is cis, more substituted. And this is less substituted. You got all 3 alkenes. Of course, trans, E2, trans, more substituted is the major, but all E2 products. Finally, a primary, a good nucleophile, Cn minus, reaction is substitution, SN2 only. This is a good nucleophile, it's a weak base. So we get substitution product. Does it make sense, guys? Guys, does it make sense?
Yes.
Right, let me see. I'm sorry?
The first reaction, isn't it strong base?
No, ETOH is ethanol, it's neutral, it's a weak base, it's a solvent.
Okay, I see what I missed. Okay, thanks.
Yes, ETO minus is a strong base.
Okay, I mixed it up, thanks.
But ETOH is a weak base, remember. Okay, that's the solvent. I mean, this one is basically cook this thing in a solvent. And we have this, it is a nucleophile, it is a base, but both are weak. Okay, both are weak. All right, let me see if I have more. Okay, these are all the reactions you guys missed, but for example, here, this reaction, the fourth one, we have a secondary. Okay, we have a secondary, but you can see that the beta is branched. So that kind of tell you this guy is sterically hindered. Okay, steric hindered. Because secondary, but the beta is branched. So hindered means what? Substitution is not that good. Now, what do we have? Strong base, strong nucleophile. If it is strong base, strong nucleophile, we have SN2 and E2. But this substrate, because it's hindered, so E2 now dominates, then SN2. You can see that. We have E2 as the major product, SN2 as the minor product. Usually SN2 is favored than E2, but this case, beta is branched. If beta is branched, then E2 will be dominant because substitution is too crowded. Okay, it's too crowded. We have a strong base and a strong nucleophile. If it's strong base, strong nucleophile, always remember they're both favored, SN2 and E2, but you have to like the substrate. Secondary, both could happen, but this secondary, there's a beta branch, meaning this carbon is actually very hard to approach. Sterically hindered. Okay, sterically hindered. All right, any questions? Let me see if I have more. Okay, I thought a lot of questions we have did in the book, and these two we even did in the quiz, I think. In your quiz, exact the same question, I think. Again, some of you may not be satisfied with the test. If you want to take a look, let me know which page you want. I can show you.
Can you send that key?
No, I cannot, sorry. I cannot send the key to you, but I can show you here.
Okay.
I can show you here if you want. Okay, this is the first page. Okay, for example, this one is what? This one is tertiary, right? Tertiary means what? No SN2. You have a what? Weak nucleophile, weak base. So you have what? SN1 or E1. Of course, this one, it showed you only substitution happened. So you're talking about SN1 mechanism. Somebody show me SN2 here. I don't know why, but again, follow these guidelines for chapter 9. I know it's a lot, chapter 9, but you have to ask yourself, this is tertiary. Tertiary, there's no SN2. No SN2 means you have E2, SN1, E1, 3. And this is a weak nucleophile, weak base nucleophile, no E2. So you're talking about SN1 and E1. And the reaction shows you this is SN1 already because it's not elimination, there's an alkene. So SN1, you find out, hey, this is SN1. What is SN1? Leaving of the leaving group first, you get a carbocation. Then water attacks the carbocation to give you the product. Okay, here also SN1, it tells you it's SN1 already here. We know SN1 is racemic. You get one product, the other one is just the enantiomer, if you can draw the enantiomer. Okay, the other product is just the enantiomer. All right, I think I am, let me at least stop recording.